Okay, welcome everyone. So I've been given the honor to present you what we can do to look for fundamental physics with multi-wavelength observations. And in general, this will be a lecture course spread within multi-wavelength and multi-messenger. And this is kind of an outline of the talk. I'll be using both slides and Blackboard, where I'll try to guide you through the main mechanisms that allow us to probe different particles in an astrophysical context. So you know that we can use multi-messenger probes from high energy radiation at multimode wavelengths, but also charged and other neutral particles, and now very recently also gravitational waves, to try to understand further the dynamic and evolution of our universe. And this is strictly linked to what alternative models of fundamental physics may be out there and how we can unveil fundamental properties of matter with high energy astroparticle experiments. So two-thirds of the course would be about high energy astrophysics, because we cannot look for fundamental physics if we don't know how, in the standard framework of standard interactions, high energy radiation and charged particles are produced and propagate in the cosmos. So this is why I'll guide you through what are the particle interactions with matter and radiation, how we can produce photons at different wavelengths, and how we can also produce other secondary particles like neutrinos and charged cosmic rays. I'll then spend a bit of time on how particles are accelerated in astrophysical sources and why we do expect non-thermal emission from those objects. And in the final lectures, I'll then introduce how we can look for new physics with an eye specifically on an example, which is how we look for dark matter in the sky. And if there is time, I will also touch upon anomalous propagation scenarios and how we can test fundamental symmetries and other secret interactions among particles. So Nicolaou kindly introduced myself, but before starting, I would like to have an overview on what is your main field of research. So who of you is working on astroparticle already? Okay, who is working in particle physics? Okay, and who high energy astrophysics? So the ones that I missed that haven't raised the hand, what are you working on mostly? Gravitational waves. Okay, for me it's astroparticle, but fine. And cosmology? I haven't asked cosmology, right? Okay, that's fine. Good. How many of you are in your first year of PhD? First year of PhD? Or younger than that? Okay, and the others are second or third. Okay, fine. Thank you. So yeah, let's get started with something that is a bit boring but needed for us to have all the same vocabulary. Here is some reading material. It's just a list of the references that I used to prepare this class. What I would like to mention about the fundamental physics test with astroparticle and cosmological experiments is like a white paper from the European Consortium for Astroparticle Theory, which might be a reference for those of you who are starting to working in the field to have a look at what the community is doing. So the multi-wavelength spectrum, as you all well know, deploys over a wide range of wavelengths and energies. And depending on where we are, different mechanisms for formation and production of these photons can occur. So below few electron volts, we can have what is produced through thermal radiation, and then above like 10 to the 6 Kelvin, we can have non-thermal radiation that is produced, and we will mostly see production through what we call the Compton scattering and synchrotron radiation, because those are the main mechanisms to produce photons at high wavelength and relevant for astroparticle physics. So this is probably a series of images that you have already seen in your academic life, which is our own galaxy, so Milky Way, seen at different wavelengths from radio, the radio continuum, produced mostly by synchrotron emission, through the infrared wavelength, then the optic through the Gaia, where you see that the galactic center here in the center of the picture is highly absorbed by dust. And then you end up in very high energy like X-rays and photons. And we will see how you can produce the radiation and why those images look the way as they look like. So in the end, what you would like to be able to explain is not only this multi-wavelength emission, but as I mentioned before, also the distribution of particles that are detected through high energy astrophysical experiments. In particular, you have that here at energies of about 10 to the 10 electron volts, so giga electron volts, you have the photons, the high energy gamma rays, as they are detected mostly by the larger telescope aboard the Fermi satellite. You then we do detect high energy neutrinos through mostly the IceCube instrument and the South Pole. And we also detect charged cosmic rays at very high energies. And what we would like to understand is what is the origin of these different particles and radiation, and how they can fit in our global understanding of the high energy sky. And the picture is even broader, because what we measure are not only what I mentioned before, gamma rays, neutrinos, and high energy cosmic rays, but actually what you see here is the all particle cosmic ray spectrum. We measure charged particles of different charge and masses, where the protons are by far dominating the flux of particle received by high energy experiments, from energies that goes from GeV up to ultra high energies. And again, the game is to understand how these different particles and radiation comes to be measured at Earth when produced in a large astrophysical environments. This means that we have to deal with very different environments that are at different scales. So we have environments that are having common the fact that matter in this environment is very diluted. So we are talking about 1 proton per centimeters cube in galaxies, and 10 to the minus 6 particles per centimeter cube in extragalactic environment. The scales are huge, so I just remember here that we are talking with the scale of the parsec, which is about 10 to the 16 meters, and why galaxies have radii about kilometer scale large. If we go to the extragalactic environment, then we are talking about scales of megaparsec to gigaparsec. And also the time scales are actually very long. We're talking about lifetime of processes of the order of hundreds of mega years in galaxies, and then to be compared with a full age of the universe of 14 giga years, if we are considering the full content. One important aspect of galaxies and extragalactic environments is that all these environments are magnetized, and magnetic field will are playing a fundamental role in depicting the final shape of fluxes as they are measured. So we are talking about magnetic fields of the order of microgauss in galaxies, 1 to 10 microgauss. In the center of galaxies might go up to hundreds. And we're talking about very dim magnetic field of the order of nanogauss between galaxies in the extragalactic space. One good reference point is to just put everyone on the same page on the system of coordinates that we'll be using. So we will be working in galactic coordinates, where the galactic center is at latitude and longitude equal to 0, and the solar system, so the Earth, is at about 8.5 kiloparsec from the galactic center, and we typically project all observations into this galactic coordinate system of longitude and latitude, and the north galactic pole is at latitude of 90 degrees. So a few words on our Milky Way, because everything that gets from far away has to come in through the Milky Way environment. So the Milky Way has a total mass of about 10 to the 12 solar masses, and most of it is embedded in the dark matter halo. We will be discussing that in some of the later lectures, while from the point of view of the luminous matter, you have about 10 to the 11 stars for a total mass of about 10 to the 10 solar masses, and 10% of it is in the form of gas, with a total mass of 10 to the 9 solar masses. The gas and the stars are typically distributed in what we call the thin stellar disk, and a bulge, a galactic bulge toward the center. But then there are specific astrophysical systems like globular clusters or other bounded objects like nuclear stellar clusters that you can find towards the galactic center. So let's then start with some basic vocabulary for everyone to be on the same page. So I will be mostly working in what we call the natural units, which is common for particle physics, not so much for astrophysics. So every time you want them to go back to units and to do whatever dimensional analysis, you have to put back all the constants. So mostly we typically work in a system where all fundamental constants are set to 1. And this also means that then energies, masses transforms in the same way, and times and length also transform in the same way and as the inverse of the energy. Typically, we keep, nonetheless, some other fundamental constants explicitly, as the Newton constant, which is also related to the Planck mass. So this is about 10 to the 19 GeV to the minus 2. So I don't have to write down how we go from wavelengths to energies, but as you have seen in one of the previous plots, we will be talking about either energy or wavelength or frequency, and we will go from one of the others. And also the secondary quantities that you can find in plots and so on might be expressed in one of these variables, knowing that you can go from one to the other quite easily. So most of the particles that will travel in the galaxy or from high energy sources are relativistic. So we will be need fundamental ideas of relativistic kinematics. So just to remind you, we will have like 3 particle momenta. which can be expressed as a function of the gamma and beta factor, where beta is the velocity divided by the velocity of the particle divided by the speed of light, and gamma is nothing else than 1 over the square root of 1 minus beta square. Can you see the handwriting? Okay. So then we can define the total energy of a particle, which is nothing else than the mass times the factor gamma, and is also the square root of the sum of the square of the masses plus the square of the momentum. We will be introducing at some point the rigidity, which is the momentum divided by the charge of the particle. And this is measured in gigavolt. And this is relevant because the rigidity, particles of the same rigidity will act in the same way under the effect of a magnetic field. And this is relevant, for example, for propagation of charged particles in the galaxy. So whenever you have relativistic particles, then we will be using different frames where either one of the particles involved in a process is at rest, and then what we want to know are, for example, the energies of the kinematics in the lab frame. So we will be often work with two different frames. One is the center of mass frame, where one of the particles is at rest, and the other is the lab frame, where energies and momenta or rigidity are effectively measured. So I'll just give you the sketch. So typically we work with two body processes, like particle A or scattering off particle B. And so in the lab frame, we can define energies and momenta, and we can also define the angle of scattering, I will call it psi, between the direction of the two particles. Typically, for example, A is relativistic and moving with velocity beta in one direction. And in the center of mass frame, typically I will prime the quantities in the center of mass frame. I hope this will be uniform in all the lectures, but just apologies if sometimes I miss it. We can then redefine the same particles. So particle A in the center of mass, where A is at rest. Particle A will see particle B impacting with some energy, E prime, and an angle in the center of mass, psi prime. So this will be used later for a lot of things. And so I just want to write here the main transformations that we will be using. So how you can go from the energy of the particle B, for example, in the center of mass to the energy of the same particle in the lab frame. And analogously, you can also have the inverse transformation, where you go from the center of mass energy to the lab frame. And we'll be use this transformation quite a lot during the course of the class. So then we are talking about very high energy particles, and there will be both collisional processes of like elastic scattering, but also inelastic processes. And for these inelastic processes, we will talk about energy thresholds. So often the interactions within different particles are possible only if there is a threshold that is met in the kinematics of the particles that are involved. So there are two important relativistic invariants that I'll be using. One is the center of mass energy. So again, if you have a process of particle A plus particle B that produce final states C plus D, for example, one important quantity that is conserved is the center of mass energy of the initial state that should be equal to the center of mass energy of the final state, where the initial center of mass energy is nothing else as the sum of the four momenta squared, and you can then just write that as a function of all the elements in this sum. For some of you, this is all well known, but it's something that I'll be using continuously, basically. Psi. And then knowing the fundamental relation between the masses, you can then express in terms of the masses of the incident particles, their momenta and angle. While for the final state, if you want, for example, to produce particles C and D at rest, this defines the threshold for this process to happen. And then in this case, this will simply be the sum of the masses squared. So by equiparating the center of mass energy in the initial state and the final state for production of this particle at rest, what you can derive is what should be the energy of the incident particle, and knowing the energy of one of them, you can derive what is the threshold for this process to happen. The other important invariant that I'll be using is instead the momentum transferred, which I'll be using in a couple of. So the momentum transfer is also conserved in this kind of processes, and this will be used. So also, again, when you have particles that are involved, what you can always define is what is the mean free path of particle in a medium. And for example, if you have, typically you have an incident flux of particles that goes onto a target, and this target has a typical microscopic cross-section, sigma, and has a given, so we'll measure in cross-sections in centimeters square, and has a typical target density of the medium. So if there are absorption effects in this medium, then what you can define is the mean free path of the particle, which is defined as 1 over sigma times n. And this also is related to the collisional rate, which often we will be using, which is nothing else than the beta, so the velocity of the particles divided by the mean free path. This is the collisional rate. And this is the mean free path in the medium. So the definition of mean free path, it comes originally, it is introduced in radiative transfer. So radiative transfer is how radiation can get emitted or absorbed, and you can solve the equation of radiative transfer in order to understand and to derive what is the radiation at point S of an initial beam of radiation under re-emission and absorption. So in radiative transfer theory, you can actually define what is the absorption coefficient at a given frequency alpha, which is nothing else than the cross-section of the process of this, so the cross-section of the medium times the number density. And the equation for how the intensity of a beam changes with length in presence of absorption is this differential equation here, and you can solve for I knowing the initial conditions at s equal to 0. And you can derive how the intensity changes because of absorption, and is nothing else the intensity at your initial point where you define your initial condition, suppressed by an exponential factor because of the absorption term. So from here, you can, this integral here is what is called optical depth, and we will be using something, the same optical depth in an application. So this is called optical depth. So that if you have a medium which has an optical depth larger than 1, this is called optically thick. So you have a strong exponential suppression of your radiation. If you have this optical depth which is smaller than 1, then the medium is optically thin. And when the optical depth is equal to 1, this is what defines your mean free path. So you can use the mean free path definition for radiation or for then particle fluxes, and this goes then back to the definition of the collisional rate. Okay, I haven't mentioned you can interrupt me, of course, at any time. This first part of the lecture is a lot of notion, but if you have questions or something is not clear, do not hesitate to interrupt me. Okay. So then something else that we will be seeing is that particle or radiation can lose part of the energy through different processes, and it leads me to introduce you about what we meant with energy losses. So you will hear a lot about mechanisms for energy losses, how these act on particles and radiation, and I'll just introduce here the main quantities that we'll be dealing with, so that then it will be easier to follow the rest. So if you consider energy losses, there is always a process associated to that. So there is always a cross-section. And when you have a cross-section, you can consider what is the differential cross-section as a function of the energy which is transferred. And you can also call it the y's, depending on the units that you use. And you can define moments of energy loss. So the first moment of energy losses is called the stopping power. And just by definition is the integral, so you can express it, so it's the energy lost per unit space. And you can define it, as I mentioned, as the first moment of the energy loss, where n is again the target density. And from the stopping power, you can define two important quantities that we'll be using. One is the stopping time, which is the integral between the mass of the particle and the energy, the total energy of the energy loss rate. This is the energy loss rate, which can be approximated just by the energy of the particle divided by the energy loss rate. The energy loss rate is also expressed here, so it's related of the cross-section of your process. And on the other hand, you can define the stopping range, which is the same integral, but this time with the stopping, energy loss rate in function of as a function of distance. So why this is relevant? Because for any given process, so often particles are subject to different processes, and in order to understand what is the dominant process to affect the most, for example, the evolution of the particle in a magnetic field or for the production of gamma rays, you need to know what are the different processes that this particle can undergo with the others that are in the environment. And in order to understand what is the dominant process, you can compare these kind of quantities in order to understand is a process completely subdominant or is this process dominant with respect to others. And this is what we will be doing for several examples. So given the energy losses, then you can define two different type of energy losses and processes. So whenever you have processes for which the main particles kind of disappear during the interaction, or transfers to the final state particles a sizable amount of energy, then we talk about catastrophic losses. And for example, inelastic processes are an example of catastrophic losses where the particles are completely disrupted in the interactions. And in this case, the loss time is about the collision rate, the inverse of the collision rate, and the loss distance or stopping range is about equal to the mean free path. And on the other hand, you can have continuous losses where instead the energy that is transferred to the particles is only is small, and the primary particle retains its main nature and also its main energy. So for example, elastic scattering processes or inverse contour or synchrotron radiation are an example of continuous losses. And in this case, the loss time is about is much larger than the collision rate, and same is for the distance, the stopping range compared to the mean free path. Okay. So next and final of the points that I wanted to introduce you are the different definitions of luminosities, fluxes, intensities, and emissivities, which are relevant because in the end, the things that you measure at Earth is the flux, either of particles or of radiation. So let me start introducing the notion of energy flux, which is the most intuitive quantity, if you want, which is can be defined by the fact that if you have an element surface area, so an infinitesimal area element delta A, which is exposed to radiation for some time, delta T, then the energy that goes through this area is proportional to the area and the time, and this defines the energy flux, which is the energy that goes through the area element in a given amount of time. So in the literature, depending on the book, you can find that this energy flux has a different letter. It can be sometimes F, sometimes S. So don't forget that what matters in order for you to not to get confused by the notation are the units. So whenever you are in doubt what I'm talking about or what I'm reading about, then just do a dimensional analysis to see what actually is the book about or the paper about, even if different papers use different notations for fluxes, intensities, and emissivities. So this is my notation for the class. Just remember to do a dimensional analysis if you are in doubt. So then this was for the energy for an area which is exposed, for example, to a beam of radiation. But then you can ask yourself, okay, what is the energy that is carried by an individual gamma rays or an individual photon? So you can define what is called the specific intensity, which is the intensity that is going through the area, and what you are interested in is the energy that is carried by a given ray over a solid angle delta omega for always a given amount of time. So the energy that is crossing this surface will be proportional to the time, to the element area, and to the solid angle. So then in this way you can define, this is basically the definition of specific intensity, where specific refers to the fact that the intensity can depend on the wavelength of the photon, for example. This is the energy that is crossing a given area per unit solid angle per unit time per unit frequency. So then if you want the total intensity, you can integrate over the frequency spectrum of your radiation to get the total intensity of your beams. And again, if you look at the dimension, this is an energy per area, per time, per steradian, per frequency unit. So given the definition of flux and intensity, then what you really typically have are sources of radiation. So you have to understand how is the intensity of a beam changing because there is an emitting source of additional energy. So what you can define is the emission coefficient. So the emission coefficient is quantify the energy that is emitted per unit volume, solid angle, and time by a source of radiation. And it can be the specific emission coefficient if you also want to, if you have it also expressed in unit of frequencies. So if you consider a typical emitting source of radiation, this emission coefficient is typically dependent on the position. And this we'll see most of the processes in our galaxies have an emissivity which is position dependent. If you consider a source which is isotropically emitting, then you can have you get the definition of power, which is the radiated power per unit volume, and this power as units of erg per second per centimeters cube. So this is the angle. This also gives you the angle integrated emissivity. Oh, no, I don't like it. So when you can re-express if you have if you want an isotropic source with as a function as two. So if you have a medium of an emitting source which has a given mass density, so this is the mass density of your emitting medium, you can re-express the angle average emissivity as a function of the solid angle, the fraction of the solid angle that you are considering. And this is another way to often find the emissivity defined depending on what you are considering as emitting source. And this d omega over 4 pi is nothing else than the fraction of energy that you take in an infinitesimal element of solid angle. So for isotropic emission, what you have is that this relation holds. So epsilon times rho is nothing else, again, than the total emitting power, just by making the two equal. So if you then look at the geometry of this problem, what you have typically is that the radiation goes along a given direction. So the volume, the infinitesimal volume, is nothing else than the infinitesimal line 1D dimension times the area. And if you remember the definition of energy flux, then from this definition here, you can arrive at the final expression of the energy flux as a function of the emissivity. So there is a dependence on where the emission is made positionally, and there is a dependence on the LB coordinates that defines your solid angle. So you can write it as 1 over 4 pi of this emissivity coefficient times your mass density times the infinitesimal 1D dimension times the solid angle. And for here you can also, as I mentioned before, write it as a function of power of the emitted radiation. And we will be using this, for example, from synchrotron and inverse Compton emission. So often, however, this holds for radiation, but when I show you the main observables that we have, we are dealing with particles, so high energy particles, for which we measure, instead of the energy flux, we do measure the particle flux. So by analogy with the radiation flux, we can go from these formulas for radiation to the formulas for particle. So if S is the energy flux as in units of erg centimeters square per second, we can define in analogy the particle flux in units of number of particles per area per second. And in the same way, we can go from the radiation emissivity of a given material or mass density m, which is what I called before the local emissivity, where local is the fact that epsilon is indeed position dependent and rho is also position dependent. We can go in analogy to that to go to what we call, what I call in my notation Q, which is the local particle emissivity, which is will be expressed is nothing else than the production rate. So the number of particles, if you want, when there is a one, is always the number of particles per volume per unit time. So it's the production rate per unit volume. And in this way, we can write here the expression of the flux, which will be typically positional dependent and also depending on the line of sight, so which is the direction that we look. These are the coordinates related to the solid angle. In analogy with what I wrote before for the radiation, and therefore we can then suppress the position dependence by integrating over this 1D dimension, which is what we call line of sight. So to keep track only of the angular dependence of the particle flux. So then this allows you to define the differential flux as a function of solid angle, which is this definition here, that depends on the local volume emissivity of what you have, or what is emitting. And often what we keep track of in experiments is the energy dependence of this flux, because typically different mechanisms contributes to the local emissivity in different energy bands. So what we also can define is the differential local emissivity, differential in energy. So typically what you have is that you will have, instead of Q, an emissivity which is energy or frequency dependence. And so this naturally defines the flux as a function of energy and angular coordinates. And this is the main observables that you need to compute in order to get, for example, what is the final flux of particles observed. Yeah. The B, so whenever a solid angle is defined by two angles, which are, I call them L and B. Typically you have phi and theta, but since we work on galactic coordinates, the solid angle is defined by those two angles. And while I'm here, yeah, I can also give you, just taking back the scheme before about galactic coordinates. So typically you can always go, if you have a Cartesian reference frame of x, y, z, where x0, y0, and z0 are defining the galactic center, then you can transform in galactic coordinates by the following transformations, which I write it here. For your convenience. So you can always go from the Cartesian reference frame centered at the galactic center to the reference frame of galactic coordinates, where S is your line of sight. So this very same S. And then L and B are the angles that enters in the solid angle definition. And here, this R is our sun, which typically is 8.5 kiloparsec. But also this number can change depending on the papers and what kind of most recent measurements they have been using for. So then you see that if you do a dimensional analysis, so this differential flux is then expressed in units of number of particles per centimeter square per second per steradiant per energy. And the local differential emissivity is the number of particles produced per volume per unit time per energy. Okay? So typically what we will see is how from fundamental processes we can compute this Q tilde here, either as a function of energy or a function of frequency. And then in order to get the final flux, most of the cases, like for galactic processes, you have to perform this integral in order to get then the flux of observable particles. And there might be other terms here that accounts for extragalactic absorption if you have processes that are produced by far-away galaxies, or absorption in our own galaxy, as in case of the synchrotron emission because of free absorption. So that is kind of the main framework where we'll be working. What time is it? So if there are no questions, then I move to introduce something which is I hope every one of you have seen at least once in their life, which is how particles moves in the presence of magnetic field. And why is that? Is because, as I mentioned before, magnetic fields are everywhere. And so in order to understand how particles propagates, for example, in the galaxy, but also in extragalactic space, we will be using some of the notions that I'm gonna introduce you now. So whenever you have a charged particle, this particle, in the presence of external magnetic and electric field, is subject to the Lorentz force. And when typically this particle is also moving. So you can express the Lorentz force classical, this way. And let's consider just the case where there is no electric field and you have a constant, large-scale, uniform field. And let's see what happens to this particle. So if you have a particle with charge z times the charge of the electrons with mass m, and that travels at a given velocity v, or relativistically speaking beta, then you can actually solve the equation of motion of this particle, so how the momentum changes with time, depends on what is the force that is acting on this particle. So you can, working out a bit of algebra, what you can show is that the velocity of the particle is related to the cross product between the magnetic field and the velocity itself. So the first thing that you see is that the velocity of the particle is perpendicular to the acceleration that is acting on the particle, which means that, as a matter of fact, if you solve for this equation, the solution is that if you decompose the velocity in, so you have the velocity vector of this particle along a direction x, and you have the B field, which we assume in the z direction. So if you decompose this velocity vector in a component parallel to the magnetic field and a component perpendicular to the magnetic field in the xy plane, you can see that the velocity parallel to the magnetic field, so the velocity in the direction z, is constant. This comes by solving the equation of motion. And if you define this angle mu is called the pitch angle. Then what you can also show is that the pitch angle is constant indeed. And so, which means that the component of the momentum, or if you want the velocity, perpendicular to the magnetic field in the xy plane is also constant, and you can demonstrate that is related to the pitch angle and to the modulus of the momentum. So this equation of motion is depicting a motion which is also in the slide here, which is this helicoidal motion where the velocity, the modulus of the velocity is constant, and what is changing is just the direction of the velocity. So this helicoidal motion is the main motion of charged particles in a uniform magnetic field, and you can define what is, for example, the radius of this helicoidal motion and the frequency of this motion. So the particles, we say that it gyrates with a given radius, and the radius of which is called the gyro radius can be derived in like a simple way. So for this motion, what you have is that the acceleration in the y-x plane, so this acceleration in the y-x plane, you can write it as the variation of the transversal velocity okay, should be equal to the centripetal acceleration that you have, and in this plane again. Which depends on the radius of this helicoidal motion. And so from here, you can derive what is this gyrus radius, which is nothing else than the momentum along the perpendicular direction of the magnetic field divided by the magnetic field. So this is the equation for the non-relativistic Larmor radius, and this quantity you will see will come back often, both in acceleration processes, in astrophysical sources, but also for understanding the propagation scales in our own galaxy and the confinement of particles in the galaxy. So having defined the Larmor radius, what you can define is also the frequency, the angular gyro frequency, which is the velocity divided by the gyro radius, and so nothing else that the charge divided times the magnetic field divided by the mass. And in the same way, you can define the frequency, the gyro frequency, which is the angular gyro frequency divided by 2 pi. And if you plug in some numbers, so the fact that the charge of a particle is z times the charge of the electron, and the mass can be compared with the electron mass, you can get like an idea of the scales of this frequency, which is also is not written there. So you see that for masses of, let's suppose we are considering electrons, then for masses of micro Gauss intensity, then this frequency is pretty low, it's 2.8 Hertz. And this was like the non-relativistic case. As I mentioned before, most of our systems are fully, in most of our systems, particles are fully relativistic, so we need to introduce the fully relativistic Larmor radius and frequency, which are also written there, but I just rewrite them. So in the relativistic case, so the Larmor radius is gamma times the non-relativistic gyro radius, and so you can work out, hopefully with all the elements that I gave you before, what here. And then if you remember from the definition that I gave you in the introduction, we can define the rigidity as the ratio between the momentum and the charge of a particle. So then you end up with the expression in the slide where you can re-express in terms of some numbers as a function of rigidity and as a function of the magnetic field intensity. And as you see, we are talking, so for typical values of rigidity and magnetic field in astrophysical system, the scale of the Larmor radius is 10 to the minus 6 parsecs. So it's really a micro scale with respect to, for example, an astrophysical object where these particles are embedded. And we will see some examples later on. And in the same way, from the classical angular gyro frequency, you can go to the relativistic Larmor frequency, which again can be expressed as a function of typical values of the magnetic field and the energy of the traveling particle. So again, the energy comes from this factor gamma here. Yeah. Yeah, you are right. No, yeah, it's only that is the non-relativistic case, and the charge is fine. For the charge, also the charge. Yeah, but the charge should be on the left here. You see, you mean here? Yeah. But okay, this is generic, so you can keep it, and then you can go to the non-relativistic case. So, thank you. So what you can see, which is also important, is that the angles, the frequencies are, so the angular frequencies are very small. So you see here that if you want to understand particle acceleration in astrophysical objects, you have to deal with the microphysics of the particle motion in those magnetic fields. Okay. This probably, I leave it there. Okay. Questions till this point? I lost my... Okay. Then what we are ready to start with is a big part of the lectures, which is about how matter and radiation are are targets of particle interactions. So the main point that we will see is that there exist different processes that can produce radiation at different wavelengths, but that in addition to radiation also brings you a way to produce additional particles like neutrinos, but also charged cosmic rays. So we will mainly see mechanisms for interaction with electromagnetic field first. And so we will have a look at how photons interact with radiation. And this has secondary implications for the production of photons at different wavelengths. And then two very important mechanisms of interaction of matter, especially lepton, with radiation, that are inverse Compton scattering and synchrotron emission. I will not touch interaction of leptons with matter like ionization and Bremsstrahlung because of the sake of time, while I will describe in quite some detail how we model the interaction of hadrons with matter and radiation. And this is because depending on the interaction, those are the main mechanisms to produce multi-wavelength photons and neutrinos of very high energy. And so this will give us like an idea on what are the main physical processes that originate photons in our own galaxy, but also photons and neutrino from extragalactic sources. And I will also show you how we can connect, for a typical source population, photons and neutrinos that comes from this kind of interaction. So this is, if you want, the basis of any multi-messenger connection. So when you heard about multi-messenger connection, the physics of it is on how particles interact with matter and radiation. Okay, so depending on the scales that we are dealing with, there will be processes that are mostly relevant for galactic scales and other processes that are mostly relevant for extragalactic objects. So in particular, what I want to retain are the different time scales that are at play. So when we talk about galactic cosmic rays, so do you have an idea of the propagation timescales of cosmic rays in a galaxy? Anyone? Does it take 1 year for an electron to propagate in the galaxy? Does it take hundreds of years? Okay, the typical scales for propagation in the galaxy are mega years. If they can escape freely, this is the time that gets to them. The number density of hydrogen, so protons in the galaxy, which is by large the largest, the most abundant element, I already said, is of the order of 1 per centimeters cube. And so the energies of, let's say, protons produced in astrophysical sources in the galaxy are of the order of GeV, 2 TeV scale. So in an extragalactic environment, instead, the propagation timescales are much longer, is of the order of the gigayear. And this is something that I already said in the introduction. The matter is much more diluted. So and the energies of, so the protons, for example, can be highly relativistic, having gammas of the order up to 10 to the 9. So it means that with this very high energy, so already with a very low diluted amount of matter, the interaction of radiation with matter are less relevant. And what you start to have are very high energetic processes where the protons carries high Lorentz factors that can then open up, as I mentioned before, thresholds for processes that wouldn't occur in a galaxy. And specifically, it will be very important to treat inelastic processes for ultra-high energy cosmic rays. So everything relies on the fact that you can produce charged particles at these energies. So ultimately, part of the question in high energy astrophysics is, what is the origin of these high energetic particles? So what are the mechanisms for accelerations in high energy astrophysical sources? What kind of mechanisms of acceleration you can have in the galaxy, and what in extragalactic environment? And this we will touch upon. This to me is that depending on the environment that you are looking at, the interactions between particles and matter that are dominant in your environment or that are open in your environment are different depending on the energetics of your initial particles. Okay. Then in the last 15 to 20 minutes, 15 probably is fine, the next big So let me go before with that, so that perhaps I can finish on time. Yeah. No, we are not neglecting. They are there. They are especially relevant for sub-GV energies. I will just, it's very, like, if you want, is a very classical treatment. Once you know the cross-section for Bremsstrahlung, so Bremsstrahlung is the fact that electrons radiate due to the Coulomb potential of matter in the medium. So once you know from the textbook, the cross-section from Bremsstrahlung, then you can easily compute the energy loss that is associated to Bremsstrahlung and the final flux of photons. So is, if you want, is much simpler than what happens for inverse Compton and synchrotron. But it's definitely one source of radiation that specifically is important for sub-GeV to MeV photons. So, yeah, before starting with inverse Compton, so as I mentioned, one important things in order to understand the processes are the energy of the primary particles. And for me, the primary particles will be always cosmic rays. So what you need to know now is that there are cosmic rays that can be accelerated to different energy. And the other very important thing will be the target. So said that we will look at interaction with radiation and with matter. So let's start with interaction with radiation. And what we need to know are what are the target radiation fields that are there. So if you work in the extragalactic environment, so this is the number density of matter, but what you also have are radiation fields. So in an extragalactic environment, there is, and also galactic, there is always a guaranteed source of radiation field, which is the cosmic microwave background, which carries about 400 photons per centimeters cube. And here, what you see here is the brightness of radiation fields as a function of the energy of the photon fields at redshift 0. And again, just for your own ease, you can relate this brightness to the number density of the photons differential in energy. So this is the differential energy density of the radiation field. And you see that the CMB is by large a very dominant source of cosmic radiation, which is peaked at about 10 to the minus 3 electron volt. 10 to the minus 4 electron volt. And then you have, in an extragalactic space, what you have is that, each galaxy is a source itself of photons at low energies. So low energies in high energy astro are optical and infrared. So stars in a galaxy do emit light in the optical band, but then this light can be absorbed by dust and re-emitted in the infrared wavelength. So if you collect all the emission from galaxies, from the different galaxies out there, this defines an ambient radiation in the extragalactic space, which is called the extragalactic background light, which has an average density of 1 photons per centimeters cube, and has 2 peaks, one in the infrared and one in the optical. The same holds for our own galaxy. You have again that this energy density, you see here, expressed, as I mentioned before, in other units as a function of the wavelength, takes again these 3 components. So the cosmic radiation background in our own galaxy is made up the CMB, as always, plus the starlight, so optical radiation field and infrared radiation field that comes from the stars and the dust in our own galaxy. So those radiation fields are relevant if we want to compute what is the level of interaction of radiation of particles with radiation. So for the extragalactic radiation field, what matters and what we see is very important is the redshift evolution of these background fields with redshift, so accounting for the expansion of the universe, while in our own galaxy, the relevant differential information is how the radiation field changes with position. So what you can see in our own galaxy is that depending on where you are in the galaxy, while the CMB is always constant, the starlight and the infrared radiation field can change sizably if you are at the galactic center or if you are in the spiral arms or more locally closer to Earth. So this means that the effect of interaction of particles with the radiation in our own galaxy will be position dependent, and in order to compute the final flux, you have to keep track of the spatial dependency of your radiation field. So you can expect already that interactions with radiation interactions depend on the target density. So interactions with radiation towards the galactic center will be much important than interaction with radiations locally. Okay. So now I will start with one of the first process that I want to touch upon, which is the pair production. And I'll then see where I arrive with that, but probably I won't finish it today. So let's start from the simple interaction. So we do interaction with radiation. So our target radiation is this extragalactic background light. And the first particle that we are going to study and how it does interact with the extragalactic background light are the photons. So we are considering high energy photons that are produced somewhat with photons from the ABL. And what these photons can do is to produce pairs, electron-positron pairs. So the question is, when can high energy photons produce electron-positron pairs? So first of all, do you think that this is a reaction that has a threshold? Okay, good. So first thing that we need to compute is what is the energy that a high energy photon needs to have in order to produce electron-positron pairs when interacting with an ambient photon from the extragalactic background light, or in general, it can be also the CMB or whatever other radiation field you can think about. Okay, in order to, yeah. This one is VHE, very high energy. And this is very high energy because it has to have a minimal energy, and we are going to see which is. So in order to compute the energy as a photon should have in order to produce electron-positron pairs, we can again go back to our invariants, and we need to require that the electrons and positrons are produced at rest. So this defines the threshold. So then if we just consider the first term and the fact that the photon is massless, we can get that, so the energies the product of the energies of the photons should be then equal to twice the mass of the electrons squared, right? In order to produce electron-positron pairs. Now, one energy, so we are given the energy of the photon fields, and what we want to compute is the energy threshold of the energy of the high energy photons. So in this case, we can then expand and get that the energy of the photon should be at least larger than the mass of the electron squared divided by the energy of the, this is equal to A2, divided by the energy of the photon field, and this is true in the electron rest frame. Okay? So, or if you want, let's say, in the comoving frame, what we will call comoving frame, because, yeah. Okay, so you see immediately that these cannot happen for whatever photons in the, whatever photon energies, but is only valid for high energy photons, and this is in the comoving frame, but what we are interested in is really the lab frame, where we can measure the energies of these photons and the energies of the radiation fields. So what we'll need in order to understand how those quantities relate to the energies of the photons that we observe, we have to consider how, so we typically are in the context of, in an extragalactic context, where we have the ABL, so we need to consider how different quantities evolve with redshift, and just as a reminder, the energy in the comoving frame is related to the energy observed today by 1 plus z, while the energy density of the, let's say, the particle density, so this is the number density of, for example, the photon fields, scales at 1 plus z to the cube. So then I will be using E prime and epsilon prime for the comoving frame, and unprimed, the unprimed notation is for the observed frame. So, Nicolau, I'd rather prefer to stop here because it will take me more longer than 2 minutes to discuss the optical depth. Yeah, either I can take 10, 5 to 10. 5 to 10 is okay? Okay. Okay. Then, so what is relevant in order to describe this? So this process effectively, how does it act? So you have an high energy photon, it produces pair while traveling into the extragalactic space. It means that the flux, the initial flux from these photons is depleted by the fact that it's producing a new particle. So there is an effect which is an absorption effect. So if you have an initial source of photons, because of pair production, you get out less photons than what you had at the beginning. So as I mentioned before, when you have in radiating transfer, when you have absorption, you can define an optical depth. So also in an extragalactic context related to pair production, you can define the optical depth of your photons. And the optical depth is a function of the energy of the photons that is observed and the redshift at which there is your source. So this is the source of high energy photons that then produce pairs to pair productions. So from the introduction before, the optical depth is also a proxy for the number of interactions that you have along your line of sight. So this is the energy of the photon in the observing frame. This is the redshift of the source that is producing these high energy photons. And one can work out the definition of optical depth, which depends on the distance of the object. So that again, there is this integral along the line of sight, but this time you are in extragalactic space, so you have to account for Hubble expansion of distances. And so you need to express the distance of your source in terms of the luminosity distance between the observer and the source, and how it gets expanded by and stretched by the Hubble expansion. And then, as before, if you remember, the optical depth was nothing else than the integral along the line of sight of this absorption coefficient, where the absorption coefficient was the cross-section times the target density. So if you want, in a more complex environment, the definition always originates from the same process, so we can just translate this integral in pair production of an extragalactic source. So there is a term which is related to the target density of photons, differential in energy, where this is the energy of the photon in our radiation field in the co-moving frame. And this is in units of electron volt to the -1 centimeters -3. So it's a differential number density, a number density differential in energy. Then when you have this process, you have to keep track of the angle. So these were for an head-on collision, but you need to keep track of the angle. So you have also an integral over the angles of this process, where psi is the angle between the momentum of the incoming photons and the target photon. And then you have the cross-section of pair production. So the cross-section of pair production tells you what is the rate, so what is the probability of interactions of two photons to produce the pairs. So this is the most general expression for the optical depth due to pair production. And now we can have a look at the different pieces. So, as I mentioned before, so this dl dz accounts for the how distances are stretched by the expansion rate. So if you have a flat cosmology, you can re-express this distance element as a function of cosmological parameters, where h naught is the Hubble expansion rate today, and you also have dependence from the energy matter densities parameter, so omega lambda and omega n. So you see that the optical depth for pair production depends on cosmological parameters. If you want, it depends on the cosmology. The other term that enters in this expression is the pair production cross-section, which is the Bethe-Heitler cross-section that is in all textbook for matter particle interactions, is typically a function of beta, where beta square can be defined depends on the energy of the photon, and then the energy of the radiation field, as well as on the angle. And what can be interesting to know is that this cross-section is maximal. So the maximal probability is about what we call sigma Thomson divided by 4, and we'll see that sigma Thomson is a quantity that enters often also in other processes. And the beta square has to be defined positive. So if we then replace the co-moving target energy of the photons into the observer frame, what we have is a generic condition on the energies of the two photons, but this times in the observer frame, which you see is related to the condition in the co-moving frame. And from this expression here, what you can check is then what are the typical energies that I need in order to have pre-production for a typical source, which is at redshift Z0. So the more we can reparameterize the optical depth, and this is the last point for this morning, you can work out the different terms and rearrange them in order to factorize in the optical depth definition so you can factorize the brightness of the target energy density, so the target field, times what is called, you can find if you work with this kind of process, the ABL kernel. So this ABL kernel, which is here Z0, describes basically how probable is this interaction rate. And here is the plot of the kernel. So here on the left, what you can see is just the target photon density as a function of energy of the photon fields. Here is dominated by the infrared and the optical of the ABL. And here, this rise at low energies comes from the CMB. Here is this kernel that I write here on the blackboard. And what you see is a kernel expressed as a function of this normalized product of energies divided by the electron mass squared. This is an astrophysical paper. You see that it keeps c square, c to the fourth explicitly. Here one, if you work out, is exactly the definition of the threshold condition. So what is the energy of the photons that you need to get this per production? And it has a maximum which has a peak. The peak is given by the fact that the cross-section has exactly this shaped peak that sigma Thomson to the fourth. And what you can check is that the peak of this kernel is where you have the maximal probability of interaction. So the maximal absorption of your photons will be given to you by this peak, which is at about twice this condition of threshold. So from this you can work out what is the target energy density that gives me the maximal absorption by requiring that this factor here is equal to 2, is about 2. And so you can work out the fact that you get the maximal absorption for energies that are related to the incoming photon energies in this way. And if you work out the numbers, you can see that at TV photons for a source at redshift 0 will get the most absorbed with optical radiation, while a photon energy at PV for a source again at redshift 0 will mostly get absorbed by the CMB. So why is this relevant is because you see, depending on the energy of the incoming photon, so the primary photon, and depending on the redshift of the source, the absorption will be most sensitive to different part of this radiation, extragalactic radiation field. And this, why is it relevant? Because in the end, what we are given is not the knowledge of the extragalactic background light. What we observe is the flux of a high energy particle, of a high energy source at a given redshift. This is the observed flux. And in order to understand what processes has gone through for pre-production, we have to relate this flux to the intrinsic photon spectrum. So what is the distribution of photons that are emitted at the source and how they get absorbed by pair production. So this is the only thing, so observation of high energy sources is the only thing that we can access to. And thanks to these observations, plus multiwavelength information, how galaxies are distributed, and models for radiative transfers, we can build models for the ABL. And the kinematics of the pair production tells us what observations or what energy band is giving me more information about different parts of the extragalactic background light. So the condition that tau is equal to 1 also define what is called the cosmic gamma ray horizon. So at what is the maximal distance at which we can see photons, and we will see that tomorrow. Okay. May I ask a question? Yeah. Yeah. So that's one of the main processes for what we call the photon cascades. So you mean the pairs, right? Yeah. So then you produce these electron-positron pairs, and those will initiate electromagnetic cascades. So they will back produce photon-photon pairs. This is not red, there is no threshold. That will redistribute the energy at lower energies with respect to the incoming photons. And this is an important source of secondary photons that comes from an initial flux of photons. So you will produce. No, it's not included. If you want, because then if no, it's not included. So you have to then add a re-emitting term. So you can work out what is again the cross section to produce the pairs, and now I don't know the quantifying mark, perhaps knows, but it's about like 1 order of magnitude lower generally than the intrinsic flux. But yeah, it typically has to be included in the calculations if you want to compute the full gamma ray flux from an high energy source. At GV. Yeah. So if you want, again, for the multi-wavelength purposes, if you have an high energy gamma ray emitting source and you want to try to constrain its nature, it is important to include cascades, but then you will have to go in a lower energy band. So if you have sources contributing to TV fluxes from Cherenkov telescopes, then you can use radiation in Fermi at low energies in order to constrain it. There was another question before, and then. Yeah, the Thomson. No, this is numeric. No, I mean, numerically is about the Thomson cross section. Thomson is defined in the non-relativistic limit, but it's just to give you an idea of a cross section that you might find in other processes. But the process is fully relativistic. Yeah, is a yeah, the energies are I think rather different, but the process is the same. It's electromagnetic cascades. Yes. Okay, perhaps we should go for lunch, right?